Hi, thank you for coming to my poster about radial motion anisotropies and their dependence on visual field location. Motion discriminability varies based on motion direction. Observers have greater sensitivity to random dot stimuli moving radially compared to dots moving tangentially relative to the center of gaze. A different performance asymmetry results from what location of the visual field motion stimuli are presented. For example, performance for motion detection and discrimination is greater in the lower visual field compared to the upper visual field. The goal of this study is to determine whether and how these directional and location anisotropies interact. We designed a two-alternative force choice task, where observers are instructed to indicate whether the target drifts clockwise or counterclockwise relative to an internal reference learned prior to the experimental session. The target is a drifting gabor with a speed of 8 degrees per second and a spatial frequency of 1 cycle per degree. The drift direction of the gabor is offset slightly relative to the reference, and the offset values range from 0.5 to 8 degrees. Each trial begins with a fixation period, followed by the target interval, when the drifting gabor appears for 500 milliseconds. Then observers have an unlimited time to submit a response. In the trial sequence shown, the gabor's drift direction is offset slightly with respect to an upper left reference direction. Each experimental session used a unique reference direction. Throughout the experiment, 8 polar angle locations are tested at 7 degrees eccentricity. These include 4 cardinal and 4 intracardinal locations. At each location, 2 radial and 2 tangential motion references are tested. The reference directions are shown for an example cardinal location and an intercardinal location. Note that the reference directions are cardinal at the cardinal locations and are oblique at the intercardinal locations. This allows us to measure performance using 2 radial and 2 tangential motion directions at each of the 8 locations. For each location, we then fit cumulative Gaussians to the response data corresponding to each of the 4 motion references. For simplicity, this figure shows 2 of the 4 psychometric fits for one location from a particular subject. We then calculated sensitivity as 1 over the standard deviation of each psychometric fit. Finally, to obtain sensitivity measures for radial and tangential conditions, we averaged the sensitivity measures for the 2 radial directions and did the same for the 2 tangential directions. Before looking into how the directional and location anisotropies interact, we first measured the effect of these anisotropies separately. The direction sensitivity bar plot depicts the sensitivity for radial and tangential directions, averaged across all locations. The 2 conditions are relatively comparable. The effect size is included to demonstrate that sensitivity is slightly greater for radial directions, and the variability of this difference is relatively small. The adjacent bar plot shows the mean sensitivity for lower and upper visual field locations. The 2 conditions are also quite similar. The majority of individual subjects have greater sensitivity at the lower visual field, but the difference is very small. To address our main experimental question regarding the interactions between these anisotropies, we compared radial and tangential conditions per location. The polar plot on the left shows the average sensitivity values across all subjects. We find a clear radial advantage at the lower vertical meridian. Interestingly, this advantage results from a clear enhancement for the radial condition at this location compared to all other locations. In addition, subjects have greater sensitivity for the cardinal conditions compared to the oblique conditions across all motion directions, captured by the data's diamond shape. The radial to tangential sensitivity ratio illustrates radial performance with the tangential condition as a baseline. The radial enhancement is clearest at the lower vertical location, but also present at 2 intercardinal locations in the right visual field. This suggests that the directional anisotropy is especially pronounced at this lower vertical location. These 2 effects generalize across individual subjects. 4 out of 5 subjects show a clear radial advantage at the lower vertical meridian, and all subjects have greater sensitivity for the cardinal conditions. To ensure that these results are not specific to the stimulus parameters of our study, we are currently running the same experiment, but with the monitor at half distance from the original experiment. This changes several features of the retinal image of the stimulus. 2 individuals from the sample were tested with these new parameters. Both observers maintain a clear benefit for the cardinal conditions, and 1 subject shows enhanced radial sensitivity at the lower vertical meridian. We plan to collect data from more subjects using this paradigm to better understand the generalizability of our results. The targets with radial motion directions have orientations perpendicular to the drift direction, as depicted in this schematic. A Gabor drifting radially with respect to fixation is tangentially oriented. Due to this orthogonal relationship between orientation and motion direction, one might ask whether the reported radial direction benefit can be explained in terms of higher sensitivity to tangential orientations at the lower vertical meridian. Observers, however, have higher sensitivity to radial orientations, demonstrated in a study by Sasaki and colleagues. They measured contrast sensitivity to static gratings and found better performance for radial orientations. Orientation, therefore, cannot explain our effect. If this were the case, sensitivity would be greater for tangential motion directions. This points to a radial advantage for both orientation and motion direction. Most importantly, this rules out that the anisotropies for motion direction are downstream effects resulting from orientation anisotropies. Our main experimental question was, do the directional and location anisotropies of motion sensitivity interact? Our data indicate that this is indeed the case. Observers have greater sensitivity to radial directions, but is especially pronounced at the lower vertical meridian. Additionally, we find that sensitivity is greater for cardinal conditions. This supports the oblique effect for motion. We are currently investigating whether this effect is driven by motion direction or by location. Lastly, we speculate that higher discriminability for radial directions at the lower vertical meridian may be related to natural scene statistics associated with object tracking and optic flow. At this location, radial motion directions might occur with greater frequency or have higher task relevance to an observer in the natural environment. Thanks again for coming to my poster. I hope to see you during my live poster presentation on Thursday at 7 p.m. Central European Time. Enjoy the rest of the conference.